Okay, should I start? The main Sourav is not here, but should I start? Huh? Okay. Yeah. No, the other reason was I wrote few points on that summation 1 over root n and so on. But the people who are asking more, they are not here. So maybe I'll just leave this for now and resolve it when it comes back. So so we'll continue with this theory of measurements, and last class was mostly motivational, and so I'll this time try to focus on something more concrete so that we can actually pick up examples and actually see really few things, at least how can it be calculated. But like this, the last class was also kind of exciting because honestly, I feel that it's far more important than teaching is or for people to get excited and about the important questions. So only 2 classes, only that much we can do. So as a result, I'm just giving you some of these references, which are really excellent references. So out of which, since most of the students are experimentalists, this is a book many of you might be knowing, but this is really, really the Bible of data analysis, classical. But of course, like finally, as experimentalists, all data we get are like just classical numbers. This is just an absolutely amazing book, really thin book, not scary. This is a great book for estimation and inference. It's an information theory book, again, classical textbook, undergraduate textbook. These are comparatively more advanced. This is a review of modern physics, very, very relevant for this school, because this is actually estimation, precision measurement with non-classical states of atoms. So all these recent things that are happening with spin squeezing and signal amplification and so on are discussed here. This is a classic book, though like only 10 years old, by Wiseman, Quantum Measurement and Control. Again, like one of the best books on quantum measurements. And then there's this set of papers, this person Janes, his series of papers who kind of set up the field. When he was writing these papers, not many understood the importance, but his work is just becoming more and more important. So Janes will be coming back over and over again if you get into this kind of estimation and precision measurements these days, particularly for Bayesian inference. So do look at that. And there's a whole collection of papers, and this is one good place to find them, actually. Yeah. So any questions? I still don't see everyone who were asking. So let me go into this theory of estimation. So as we just kind of quick recap, what we discussed is that we have a system with a variable x. We are actually measuring, and in the process, we are getting a set of data. And our primary interest is to actually estimate a parameter theta, which the system state actually has. And in fact, you can go into further details of it. So you might prepare the state, then pass it through a particular structure which gives this parametric dependence of theta. And then the question is set up a measurement to get an estimate of theta and estimate the error in your analysis. So this is kind of the starting point. There are several different methods of doing this estimation, out of which I'll primarily talk of 2 ways, 2 methods. The first one, let me get started. This is just kind of a little intro, but So this is what would traditionally be called method of moments, where actually the point being that we are measuring certain operators. So this is the system, this is the measurement. So we are measuring certain variables or operators depending on whether we are in the classical or quantum scenario, and we actually have this measurement results, like some average that we talked about, and this operator or this variable of the that we are measuring is not necessarily contains the parameter. The average of m is not the parameter, but there is some theory which connects this measurement result to x, what we were talking of in the last class. So basically, there is a underlying model usually in your system which connects this theta to m, and you can use this to estimate delta theta, provided you have measured and you have an estimate for m. So for example, you might have some sort of a distribution like that, and there some sort of a functional relationship between m and theta. I'll just give an example which will make it clearer. So, and there basically, you know, you have this estimate along with a variation. You know, so this is basically your delta m that you're doing from statistics of your data, and from here you can see that this will actually, you can if you know this functional relationship, you can actually calculate the corresponding estimate along with, you know, the corresponding variation delta theta, and that will actually give you the estimate that you are after along with the variation. And this is basically just, you know, like there are some conditions you need to satisfy. For example, if this functional relationship is well behaved and differentiable and so on, so you can just use a very simple linear kind of argument, say that, you know, I'll look at this angle, you know, if I can draw that. So this tan alpha is delta m over delta theta, but that's also equal to that derivative. This is the condition for you know, the function makes smooth at that point. And with that, you know, it's a very simple argument which just gives you an expression for delta theta in terms of your measurement variable delta m. And if you see, like this is I think it's so simple that normally people will call this error propagation formula. You can see it in many different ways. You see that you're trying to estimate this parameter delta theta. So this delta m is the error that you're getting from the measurement. But of course, delta m, you're measuring something else. So this you can look at it as a scaling factor, which basically, like, you know, or a unit factor which sets the right unit. But also, you know, though this formula is very simple, you can actually from last class description discussions, if you kind of appreciate delta m's and all that, so you can actually see that. Let me put an average here. So that this is the variation root mean square of the measurement, and a large effort, present effort these days is actually to see theory of estimation from this perspective. So all these different people who are trying to have better and better measures of like fine structure constants and so on. Like, so one way people go ahead is to actually make this delta m very small. So you will hear terms like squeezing and so on, collective squeezing, and those are all towards trying to make delta m small so that you have a small delta theta. But alternatively, you can also amplify this denominator. So this is squeezing, this is amplification, you know, and if you can somehow amplify without adding significant noise, there's a very fundamental argument in quantum optics, which says that any amplification or loss process actually adds noise. So if you can actually do that amplification in a way, of course, amplification will add noise, but if you can do that in a way such that, you know, the noise you add, you take it back in some two-step process, then you can actually increase this signal, and that way decrease delta.
This statement is very correct.
Uh-huh. 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 Well, yeah, so it will go in the, yeah. So not only amplification, but also losses add noise. One way of understanding, well, it will become a quantum optics lecture then, but one way of seeing it is like the way we tend to like normally a simple way of understanding quantum noise is that, you know, like one of the very fundamental things about all this amplification process is like photons and so on, is that the commutation relation needs to be satisfied, right? But the moment you have some sort of a signal amplification, so you see that this A daggers, each of them are getting multiplied by some actually, like, so it might be to the power alpha z or something, right? Some factor. And the moment you have this, yeah, yeah.
So in that case, how do you do it?
Redistribute, that's a slightly more involved question, but I was basically at a very basic level, I was first saying that the moment you have amplification or losses, your commutation relation is messed up. And one way of looking at it is to balance the commutation relation. That is the, like, it will have to be satisfied. So you have some additional noise terms, and that kind of adds to. So that is one way, but of course now you can make it more interesting in the sense that you can actually redistribute noise even in presence of amplifier. For example, what happens in parametric amplification and squeezing, that you are actually redistributing within the same system, you are actually two orthogonal coordinates, you are actually redistributing the noise by, yeah. So those are not just this, but any kind of loss, like where this amplitude is going down or gain, will always be adding more. Yeah, that is another way of saying that. Yeah, exactly. Yeah. And that non-hermiticity, like, you know, like quantum mechanics is Unitarian Hermitian. So basically that non-hermiticity is acknowledging that there is some other amplifying or lossy signal, which is basically messing it up. So, so let me do a quick example of this. You know, since it's short, so best is to like just go through. So this is a very simple kind of an example where you have a polarized light falling on a detector, and you put some half-wave plate, you know. So depending on the angle of the half-wave plate, the polarization will rotate twice of it. So so basically, you know, you have this at a particular angle, and you put a beam splitter there. So actually, like, which is polarizing beam splitter. So that means that the vertical polarization will go to this detector, and the one that is along the plane of the thing will come to this detector. So let me call this, you know, detector 1 and detector 2, you know. And so this is a very simple simple measurement, and one of the first things we learn, and basically each of the what the detectors will see, this is basically you will measure the intensity in detector 1 as you know, cosine squared theta and sine squared theta. This is Malus law, you know, and you see that classically right away, you know, you can actually define, like, get the estimate in various different ways. For example, this one estimate, which is basically I1 minus I2, is divided by I1 plus I2, gives you sine and cosine 2 theta. So this basically, you see that theta, if you actually take this functional form, divided by the total intensity I naught, which is I1 plus I2, this actually becomes an estimator. And you see that like this functional relationship is not really like this mean and so on that we are talking about. These are rather complex structured that way. But nevertheless, you can use this to actually have this kind of a structure. You can actually, this is an example which works even for single photons. Like you can actually send in like one photon at a time, and that's very classical, like coin tossing. So you will basically have a probably like, either the photon will go here or there. And again, like this intensities I1 and I2 just gets translated into probabilities. So you can actually, for example, construct I was asked to write a little below. So you can actually construct these probabilities. For example, the probability of seeing one photon in detector 1 and 0 photon in detector 2, given the angle theta is basically cosine squared theta. P01 theta is sine squared theta. And P11, P00 are 0 basically. So given this, you can again construct this and like basically these are the number of counts you see, these histograms you are talking about in the last class, so N2 minus N1. And this is your functional relationship between, remember that these are all like classical numbers, like you are actually seeing a certain number of counts in this detector, a certain number of counts. You can turn on your detector, take the data for a certain amount of time. So you can actually calculate now, this, so you can, you see that basically the measurement is just, you can calculate a measurement operator, which is just this N2 minus N1. This N2 and N1 are just number operators, A2 dagger, A2, and so on. So you can calculate M average. And this is all averages in single photon states. So this is again N cosine 2 theta. And you can also calculate delta M square, which is M square minus M average square. And this is basically, if you calculate this, again, you can take this as a homework. There's just some commutation you need to arrange. But if you do that, you basically get a N square cosine square 2 theta plus N sine square 2 theta from this. And then you have minus N square cosine square 2 theta. Right? So this and this cancels. And it is very important to note that this M square average had a N sine 2 theta. Right? So it goes as N, and that's the part where you're rearranging the commutation. So now, given this, you see that you can now use this part to estimate. So now your delta theta estimate, this is like this method of moments, delta M. So this is basically square root of N sine 2 theta divided by N del theta of cosine 2 theta. So this, if you see, the sine 2 theta cancels, and you basically have this 1 over square root of N. Right? Which is basically just a thing that you can calculate quantum mechanically, a very, very simple like harmonic oscillator kind of commutations to handle. But nevertheless, you see the same result that we were getting earlier, or we have not gotten any result, but we were discussing earlier. We'll do this kind of a thing more carefully, hopefully today. But it's basically, you see that you're sending one photon at a time. So in fact, this probabilities P1, 0 and P01 are exactly like coin tossing. You either see a click or do not see a click, except there is this cosine square sine square theta relation. So this disconnected set of photons Otherwise, just gives you a very classical result, like 1 over square root of n. They're just independent experiments. And this estimate, you're also getting from a fact that there is an underlying theory, which is the Maxwell's equations, which is the wave nature of the photons, which are giving you this. And that is what is connecting the thing that you want to estimate with the thing that you're measuring. Any questions up to this point? Okay. So we'll come back to this. Let me just leave this at this point, saying that the utter simplicity of estimating from some function that you have for your model, actually this kind of a way of method of moments has its own kind of various different kinds of constraints. It's the main problem is that, as we were last class we are discussing, that one of the things we'll be very concerned about, or rather the community is very concerned about, is there a fundamental limit to this precision that we can measure? Is there, and it turns out that since we do not have much time, there's nothing much to hide. It turns out that there are limits you can actually put. And for example, a very well-known one that we'll hopefully do today is this Kramer-Rao bound. And those kind of bounds, you would expect your measurement is such that it will saturate. But if you are actually calculating it in this way, we'll see that very clearly the moment we do Kramer-Rao bound, it not necessarily saturates the bound. So it has its own issue. There are, like, if the function is a little ill-behaved, like basically this first moment doesn't capture the whole story. So there are these issues. But nevertheless, you will see that any of this modern atomic precision measurements you open, it will start with this, and basically, like this error propagation. If you know about the system very well, and you know that you can take large number of data points so that n is very large, you can basically, like, this kind of works out. But good thing to remember is that this is not a foolproof thing. It's just taking like a tangent. So just the first derivative, it's approximating a curve with a line, and you pay the price for doing such things. But let me get to the main point that time just, oh, and I didn't start this also. Yeah. Yeah.
So when we talk about this delta theta, when we say that error propagation, so aren't we like interested in the error in M, right?
We are measuring error in M.
Yeah.
Right.
So,
and we are inferring delta error in theta. So
when we find the error in M, we can find the error in theta up to this tangent.
Slope.
Tangent only, right? So how come this like this relation that 1 by root over n, that we say it's classical, like that's the classical thing? Like
this is, you see that what is n? N is actually the number of repetitions of an experiment.
Okay.
The experiment is quantum. Every experiment is a single particle being detected, no matter how classical it looks, but it's a quantum particle. But the n is a classical repetition of a quantum experiment. So there is nothing quantum about n.
Okay.
Right. That's kind of, again, the part of that motivation that, but instead, if you would have taken n such photons and could have like quantum mechanically correlated, if you could have put them in an entangled state, then this n would have had a quantum significance, and then you would have expected that you could beat that. But as far as now the repetitions are concerned, they're just classical.
If I would have had like some kind of correlation, as you were saying, that entanglement, suppose in photon, then if I would have got the same kind of result, I'm just saying for 1 by root over n, then I can't say that it's a classical thing, right? Then it would be like it has a quantum.
You are saying that even if you have correlated, but you're still getting 1 over square. That is actually a very interesting point. In fact, that's why I was trying to be careful. Like discussions, like I don't mind if it goes in discussion, because you guys can always go and read. So let me just make this statement anyways, that when you are taking this n photons, right, they are independent in this experiment, but if you correlate them quantum mechanically, not all quantum mechanical correlations are technically what would be called metrologically useful, as in like useful for measurements. Okay. So this is a classical result and a classical bound. This is actually, it turns out this, we'll just do this. This 1 over root n actually saturates the Kramer-Rao bound. So it is actually, it is a very good bound classically, as long as you have classical correlation. And anything that improves above that, requires entanglement, but there are quantum correlations. You might correlate them, but you still might not find any improvement. So basically, as a result, many people take this enhancement above 1 over root n. So you might actually be getting a scaling which is like some gamma, n to the power gamma, where gamma is larger than 0.5 as a measure, or not, I should not say measure, but as a witness of entanglement. Okay. Like useful metrological entanglement, right? So I might have created an n particle state, and I am not interested in measuring entanglement, but I am just a precision metrologist, and I'm measuring delta theta. But if I see a scaling, I would actually say that I have a witness, I am witnessing entanglement because I see a scaling above. Does that make sense? But not all quantum correlations will give you enhancement.
Okay, thank you.
Yeah. Any other question? Yeah. Okay, so let me get to the real thing, which is the workhorse, which actually in a way we used it in the last class also. This is this method of maximum likelihood. And this is due to, there are too many Fishers in physics, but this is a Fisher, Roland Fisher. He worked in many different fields, not much in physics, but whatever he did, like kind of polymath, but of course a kind of a father figure in statistics. And these are like, like 1920s work, but it just has been a workhorse for experimentalists, but also it kind of made a whole new avatar coming back through this machine learning and so on. So effectively, like people are getting back to this. And let me state here where it starts from. So if you see, like, again, a part of the recap that we are talking about, that one way of looking at this parameter estimation is that we are updating the knowledge of theta, right? So we start with some information about theta, which might be no information, and we need to know how to characterize that. But with subsequent measurements, we are constantly updating our information. This is one way of looking at it. And this is what I was writing as the fact that what is my theta, or what is my distribution of theta, the parameter that I'm trying to estimate, given that I have a data, I have taken a measurement, and this is basically given by this factor, which is the probability of getting the data given a parameter times the probability of the parameter divided by probability of xd. Basically, p xd is just summation over theta probability of the data. This Bayes theorem, we wrote a version of this in the last class. So this part, let's make sure that we are in the same page. This is basically updating the parameter value given xd, right? So this quantity, if you see, it is actually telling you what is the probability of getting this data set that you have gotten. You might have gotten a string of data, given a parameter theta, right? And this is what is called the likelihood function. For various reasons, I should not go too much into it, but likelihood of getting the data, and there's a reason it's called function, because the Bayesian would like to view this as would like to make sure that no one really interprets this as a probability in theta. If you add up in theta, it's really a function of theta, but not a probability, and then, as I was saying, that for Bayesians is very important that this is basically this P theta is a prior, or one can also say degree of ignorance, and finally PXD is this, like this is basically just a normalization in the denominator, and this is what the Bayesian would look at, and they would say that the whole point of taking a measurement is that you're updating your distribution. You're actually making your distribution of P theta, given the data, actually better and better. Whereas the frequentist, the usual way, for example, physicists also think, they'll say that no, there is no so this is another major point of contention, that they'll say that no, there is no distribution of P theta, because theta is a parameter that is kind of God-given. There is a theta naught constant. And we are basically, what is variable is the data, right? So they'll take this as the point that the data is probabilistic, it is variable, whereas theta is constant. And because there is somewhere a real theta naught, it might be your fine structure constant or something. There is a real number needs to be found, whereas the Bayesians would say that is meaningless, because all parameters and all values are based on the experiment, like observers' knowledge, and there's nothing other than that, So and the calculations are very different, right? But nevertheless, you can look at this likelihood, maximum likelihood in different ways. But let me state, since time is just flying, the principle, principle of ML, maximum likelihood, that it's basically states that the best estimate of theta, we are still trying to find the estimate of theta, is the value. I'm just writing it following the standard thing, is the value theta estimate, that maximizes the likelihood function. So this is due to Fisher. So basically, what what the statement is saying is that if I actually look at in this theta space, and if I look at this function P theta, or whatever we are calling it, Px theta, so this, as we change theta, this will have some distribution, right? And if you see, it's very important to understand this kind of curve. So this is P theta, this is Px theta, the likelihood, and this is theta, and every point here is a probability distribution. We are actually drawing it in a parameter space. So every point is a distribution. So maximum likelihoods is saying something very straightforward and simple. It's actually saying that you basically find the maximum probability for this data that you got, your XD, and this right away gives you the estimate. This is basically the estimate. Yeah. I was planning in the last class, but I can quickly talk about it. Yeah. Yeah, but the last class was very nice and a lot of discussions. But then I realized that, like if I do not do maximum likelihood estimation, will go. But yeah, Shannon, I'll just come back maybe at the end, because at least as far as the estimation is concerned, there's a very nice way of understanding what particularly the Shannon channel capacity works. So it has a very one-to-one, this patches filling up kind of. Mm-hmm. Oh, that is a sampling. Yeah, sampling is, but even before that, like like noiseless data communication, and that has a strong connection with the fact that there's this noise patches, and we are also kind of trying to do that. So,
look, sir.
Yeah.
So when we are saying that we are talking about Bayesian statistics,
So is it that instead of like frequentist,
We are not presently, you finish your question, but before that, this is all Bayesian. If I was talking about updating p theta, presently, when I'm stating maximum likelihood, I'm only concerned about this function. And this function, this is basically a function px d theta, and you're maximizing it. That is giving you an estimate. This can be understood both in Bayesian and frequentist. The Bayesians will not stop here. They'll use this to go and maximize this a posteriori probability. So they call it a map instead of maximum likelihood. But effectively, this process is just maximizing this. But yeah,
what I'm asking is that here we are assuming, like we are believing that there will be a distribution of theta also. There is no true value of theta, right?
So that is if you're doing a Bayesian.
So now, is it the statement that instead of taking a mean value, we are taking all the moments into consideration, like frequentist, and we are saying this statement?
No, where is the number of moments consideration is not
so
frequentist or
when we are saying like there is a real theta value, that is like mean value, but we are not talking about any other values.
You can calculate from many different things. The question is, this theta that you're estimating, is there a real theta in your system that you're trying to measure? Or whatever estimate you will get, right? You will always basically have a probability distribution of p theta, some sort, and you will basically be getting some sort of a distribution. And like you can actually choose some sort of a delta theta width and between and somehow like you can just agree on some sort of a range of theta that sets your data and some mean value of theta. But that doesn't like basically the Bayesian statement is that theta is always a random variable, whereas the frequentists believe that theta naught as a constant and only your data are changing, and accordingly you basically change your distributions and so on. So this is the main primary difference or primary.
Yeah. So what I'm saying that if I say that the frequentist statement is that there is no other moment except mean value, and that mean value is fixed in Bayesian statement.
No, like like mean has nothing to do with this theta. You see, we just did an example here where this is not really theta is not really the mean value of your measurement, right? Like it just turned out that in the last class we talked about mean values, and if you're actually if your model is underlying that of a Gaussian normal distributed, then mean and standard like sigma is what you're trying to estimate, but it's not necessarily mean, right? Like it can be very complex functions.
Okay.
Okay, so how the maximum likelihood works? You basically need to maximize a function, probably a multi-parameter function. So basically, let me just kind of write quickly the steps. So you first construct, you're trying to construct this function. So construct the function. Remember that this function p xd given theta actually is a statement about the probability of getting or likelihood of getting the data given that you have a parameter. So this is basically L. I'm calling this as L theta xd. This is a function. This is what usually you will find in literature, the likelihood function. And this is basically the product of the probability of getting xi theta I equals 1 to n. So this is basically just the probability of getting a particular realization. And you can keep thinking of a binomial or Gaussian, the underlying model for getting this. And so then you actually take the log likelihood function. So you basically take the log of this likelihood function. Should I not, maybe I should not use this terminology. I don't know if this is this confusing? This is what you will find. This is why it's called likelihood function, because you see that it is now a function of theta. It's just another way of writing exactly the same thing. It's just acknowledging that this is a function of theta, not a probability of theta, because if you integrate this over d theta, it doesn't add up to 1. This is a function, but you are actually going to maximize over theta, this function, you know, so it's not. So basically this, you see that the advantage of taking the log of a product is that this is actually just sum. And then you can actually just take this to maximize. You can take this derivatives. And if you see here, J so basically, this is just reminding us this parameter, since we are writing it generally, this not necessarily is just a single parameter. It can be, in principle, many parameters. For example, a Gaussian, where you have like 2 parameters and so on. So you need to basically maximize this function for all these different parameters, you know. And at this point, you know, let me just quickly, I think that's the best way of doing it, at least stating the results. Let me just introduce.
Saikat, just to make sure that n product, that thing is for n independent trials that you're doing, right? N independent.
This?
Yeah.
Yeah, these are all independent trials. Yeah, exactly. Yeah, these are all like, yeah, so that technically I think people will call it IID. So this is independent but identical distributions. Yeah, if you open any of these books, they'll repeatedly say IID, which is basically also, I was looking for Sourav, but he has not showed up. So this is just, since you made that statement, those discussions we were having earlier on, you know, those splitting up into boxes of 100 trials and then just rearranging and making different pairs. That's a problem. Basically, that they will not be IID, they will not be independent. If you just keep playing the game of trying to bluffing the statistics. So there is a very important thing, and you know, at this stage, I hope that you guys got the spirit and will read more. So let me just at least introduce the things that are important, and whatever you're doing, you will come back to these things. So there is something called a covariance matrix. I'm just kind of introducing it out of the blue. So matrix I'm representing by hat. And so, for example, the diagonal terms of the covariance matrix are just, you know, the variance of sigma square theta. You just take it for now. So this is basically, I mean, you know, theta, this is the ith parameter. So this is theta I square minus theta square. And the off diagonal terms are basically just covariance of theta I theta j. You know, so average of theta I theta j minus theta I and theta j. So then if you take this as a definition, there's just like kind of shifting this thing. So then there exists a matrix, you know, a H matrix. People will call it a Hessian, you know, which is whose inverse and negative is this covariance matrix. These are like all our familiar quantities. And this H matrix, if you look at the ijth elements, this actually turns out to be delta 2L, delta theta I, delta theta j. So something in those lines, you see that these are H matrix is actually defined with respect to the derivative of this, the likelihood function, you know. So again, like this is starting to get abstract. So I'll just quickly use, or should I? So let me, as an example, so that we are on the same page, let's just consider like two matrices, theta 1, like the two parameters, like a system where you're actually estimating just two of them, you know, and in that case, you see that basically this, you know, this log likelihood function is just log of L theta 1, theta 2. This is just kind of simplifying the notations. It will just look a little simpler. Exactly everything that I have done there, I'm doing here. So I'm actually expanding it around this estimates, theta 1 and theta 2, right? So I have estimates, these are the estimates, theta estimate 1, and this theta hats I'm using for estimate, and then you have this two summation, we had a sum over j, two quantity, two parameters only. So first deviation, and then we have a term which is the second derivative. And these are basically, let me just write them as delta theta I, delta theta j, where this theta I is basically theta I minus theta I, and so on. And you see that principle of maximum likelihood is basically saying something very straightforward, that this quantities just drop out. And so you are actually left with, you know, first and foremost is to see that you're left with a term, you are left with something which looks like this. These are at the estimates, and then you have something like ij, these are all 1 and 2, hij, and then you have this delta theta I, delta theta j. This H is that H matrix. That's like 1 to 1. I've still not shown like how this covariance actually relates. And I'm just like using this maximum likelihood optimizing. So this actually symbolically, I can write this part as some, you know, ket or some basically like row and column, U, H, U, these are matrices. So this is, U is basically, in this case, this is just delta theta 1, delta theta 2, and delta theta 1 being just this, you know, the difference between like theta I minus theta I average, right? So given that, you see that, you know, this likelihood function actually looks like so I have replaced now, sorry, I'm going a little fast, but I have now went back and replaced this C. So you can actually maybe start seeing that this H and C connection, because this is the log likelihood function at the maximum with the maximum likelihood estimator. So this is the part, and this is the log of that. So you can start seeing, if you go back to the likelihood function that we are writing here, so that goes as exponential of this part, right? And can anyone guess, like, how does it look like exponentially? So it is, you know, if I write it here, so you see that the likelihood function, you know, here I have theta 1, theta 2, and I have given the data. So that actually goes as exponential of C inverse U. So, so this is actually a Gaussian, just it's a multivariate Gaussian. In fact, this is something, probably it's not a big surprise that we are actually kind of optimizing and trying to construct this function here. So around a maxima. So for example, this, you know, you can actually see for each of these variables. So for example, for a single variable, if you had just a single parameter instead of two parameters, P theta or L theta XD. This actually is just e to the power minus theta estimate squared divided by 2 sigma square theta. So this is actually like all are Gaussian. So this is one of the first things you see, that these distributions, once you maximize and under certain conditions, it just basically starts looking like Gaussian distributions, which is kind of a nice thing, right? So, so this is basically the, how long do I have? Till 6, no? So let me just then, so you know, a part of this was notation, but let me do a few examples to see how this maximum likelihood, which is a major workhorse, how this works. So, for example, let me take again discrete and classical non-discrete cases. So, for example, you have a game where suppose you have a box and you are given inside the box you have 3 coins. You know, this has a probability of head 1/3. This has a probability of head half, and this has a probability of head of 2/3, right? And you basically go in and pick up a coin at random, you know, and you start tossing it, and you toss 80 times, and you get basically, you know, you get 49 heads and 31 tails. And given this is your measurement, you know, you would like to make a good estimate of which coin you have picked up. Have you picked up this, that, or that? Right? And if you see, like, since coin tossing is exactly like the single photon experiments, I'll leave it as an homework. You can imagine a very realistic experiment even with photons and their nature of sources, which are basically characterized with this rate of the photon emission, to exactly do an experiment in the lab to guess that. And basically, if you do this, how would you do it? If you're following Fisher, you would basically just calculate the maximum likelihood. And just like you will calculate the likelihood function for each of these thetas, which are P, you know, that's the parameter of your theory, and you should see which one is the maximum. So let's quickly do that. So that, you know, like, so that not always you need to do this kind of optimization. You can do it directly for discrete cases. So for example, you're calculating what is the probability of 49 given P is equal to 1/3. And this is basically 80 over 49. These are just coin tossing. So there's a model behind it, which is a binomial. So you have 49, 1 minus 1/3, 31. And if you calculate this up to second decimal places, this is like 0.00. If you do the same thing now for P equals half, you know, and basically replace 1/3, 1/3 by half, you will actually, like, this number turns out to be 0.02. And if you do the same thing with the 2/3, you get 0.05. And this is clearly has a larger probability. It is like in this kind of a case, it's very straightforward. You're actually making a decision. You're actually inferring something about which coin you picked up just by calculating these probabilities and seeing which one is most likely. Right? You could have had a different problem, for example. For example, you are given like one coin, right? And you are just given one coin. You are not told which, like whatever, like you're not supposed to choose from this 3. You're given a coin, and this is the measurement result you got. And given this toss and this thing, you are asked to estimate a reasonable value of P. So this can be another problem. Okay. So you do not know. So again, you calculate the likelihood function, which is actually the fact that you got how many heads? 49, and you don't know P. So you basically use the same thing. And if you take the derivative now with respect to P, very straightforward thing. You basically get something, let me just write the last few steps. So P48, 1 minus P30, 49 minus 80P is equal to 0. And again, these extremal points are starting to show up, P equals 0, P equals 1. The similar arguments, maximum likelihood actually does a very bad job in the extremal places, but those are details. You can go back and read. But basically from here, the reasonable value you get is just 49 over 80. So this is something you could have guessed otherwise also, but you are actually doing it, you're seeing it as an application. And you can also see that this is basically in this kind of cases, discrete cases, this is basically success over total. Something like very reminiscent of the frequentist way of looking at probabilities, But let's take now the very important example, which is, kind of our usually bread and butter, that you have a model which is not binomial and discrete, but you have a model which is saying that the underlying distribution you're drawing your data from is a Gaussian, right? So you have a set of data. So this is example 3. You have a set of data. So your data, we are back to this xn, and you have a normal distribution Gaussian with mu and sigma square from which you're drawing the samples. Right. So you basically, you want to estimate now these two parameters. So your theta1, just now what we did is mu, and theta2 is sigma square. And you want to estimate this two by the same maximum likelihood. Right. And basically you optimize, so let's do the first one for theta1 equals mu, So you actually do the same thing. You construct the likelihood function. Okay, so let's just quickly also construct the likelihood function, which is, it's drawn from IID. So it's y1 to n. xi minus mu whole square divided by 2 sigma square, So the log likelihood function is just, you can calculate it. You just take the log, but since this is very important, let me just write it so that you get a start. Minus 1 over 2 sigma square summation xi minus mu whole square. So basically, you want to now take derivatives, a kind of routine thing, del mu. If you do that right here, you can see this goes as sigma square summation xi minus mu is equal to 0, which actually basically gives you an estimate of mu, which is just 1 over n summation xi. So this is your estimate of theta1. And you see that this is the thing, that estimates are just functions of data points. This maximum likelihood, so the best estimate of theta is the value theta estimate. This theta estimate is also a random variable because it combines the data points to actually give you a value, exactly what we did for the coins, what we did for now doing. So you see that this is just comes out to be a combination. It just happens to be very trivial, that it's just a mean. And this is one of the reasons this mean kind of keeps coming back, and we somehow initially, when we are first doing experiments, we tend to think that all measurements are basically mean of data points, but that's not the case, as we talked earlier, that you might have a different connection. And basically, you can calculate the average of mu, which is 1 over n summation average of xi. This is reminiscent of what we are talking in the morning. So this is n mu divided by n. which is actually mu. Mu is a parameter in your distribution, and this is your estimation. So you see that your estimation of the parameter is exactly equal to the parameter. And when this happens, you say that, oh, I have a very good estimator. I have an unbiased estimator. And all this somehow for mean, and many people just get, like many students just get stuck to the mean and doesn't move further. But for mean, it looks kind of trivial and obvious, but very quickly it changes. For example, if you actually, instead of, if you try to estimate the second parameter, theta 2, which is sigma square, you basically find, you again do del L del sigma square, take the derivative with respect to sigma square, and this you put equal to 0. I'll skip all the steps. This actually just gives you sigma square estimate is equal to 1 over n summation xi minus mu whole square. Again, very, very suggestive. You would say, oh, this is like obvious. But actually, it turns out that what is kind of, this you can try, again, just an extension of that thing, that sigma square average, exactly calculating the average the same way through xi's, is actually not equal to sigma parameter that you are trying to estimate. And this is where first in statistics you start seeing that things are not as trivial as it sounds. This is actually not unbiased. When you're estimating that parameter, your maximum likelihood is failing. It's actually not unbiased. In fact, you can actually show that this is equal to, n minus 1 over n sigma square. And you can calculate actually then an unbiased estimator, which is like 1 over n minus 1 times that. It's basically, I put this under quotes, that Fisher, when he was stating the principle of maximum likelihood, he was saying the best estimate of theta. Best is an English language word. What does one mean by best? So there are a few criteria. One of the criteria being that it needs to be unbiased, that at least the expectation value of the estimator, that is, you combine the data points to construct an estimate, that should at least in principle give you the real value of the estimate. It's a different question that what is the variance of the estimator, and that's where the game is, but it should at least give you the real variance, and you can actually in principle calculate all these coefficients, of the Hessian, which is, this del 2L, del theta 1, del theta 2, like, so this would be H1, 2 element and so on. It's just a 2 cross 2 matrix. You have a question? So you can actually calculate all these elements, and remember this H are the curvature of this, this log likelihood function, whereas C is this covariance matrix connected to sigmas. So, and if you actually do that, what you find is that, in fact, like this is very straightforward and extremely instructive. So I would say that if you had a little more time, we could have just, like, it's just really 2 lines, but let me write the result anyways. So, so basically, you find that this sigma, this is n being the total. I think I'm combining capital N and small n, but n being the total number of data sets. So it's actually n over sigma square, n over sigma 4. And you see that this h, the curvature of this function, because it's like a kind of a second derivative, is actually related to the inverse of the width. So you can, so it is actually inversely related to the covariance matrix. So in fact, this kind of cases you can actually show, you can explicitly calculate this to show, like, that these widths are connected. So just to state this, you can just invert this matrix. to find the covariance matrix to be so remember that the covariance matrix was defined as the diagonal elements being the variance of theta, that particular parameter. So you see that this is basically the variance of theta1, which is basically the variance of the mu for the Gaussian that you estimated, right? And this is what we were spending time in the morning, the sigma square over n. So actually that same n, like I don't know, I'm shifting between capital small n, So that's the variance of theta, whereas this is the variance of sigma, basically. So this is the variance of sigma square. And the covariance between sigma and mu are 0, and you can just see from here and take the derivative and find that they're 0. So this kind of, we very quickly did 3 examples. This example being something that we are already, even in the introductory phase, we started talking about it. But nevertheless, you see that they are kind of very important in many different ways, besides the fact that you actually get what would be the variance of your estimate and all that. You see that 1 over n scale, or the standard deviation goes as 1 over square root of n. That comes very naturally about this maximum likelihood. But there's also another very interesting thing that if you actually see that there's some sort of a geometry kind of starting to emerge, because you see that this maximum likelihood actually starts at the maximal point. Actually, the function is pretty much set. It starts looking like a Gaussian. With this curvatures being set by this Hessian matrix, del L del thetas, and that's actually inversely proportional to the width. So it's starting to tell you that whatever the width you get is actually deeply connected to the curvature. And this is a big hint, which eventually tells you, now you can start asking that, since all of this is finally a function of this likelihood, and it seems like how well I can do. Actually, literally, these quantities are coming from this, which are coming from this. So if I actually can somehow optimize this curvature, can I do something very fundamental? Can I actually find a fundamental limit? So is there a fundamental limit of measurement? And that's actually was something which was understood in 1940s or 50s, and that's actually also very crucial today. And that's the last thing I think I'll point out before. How long do I have? I started late, but the main person is not there. I don't know if I'll get more time. So this is, so we are basically asking, are these elements bounded? Kind of a hard and otherwise sounds very hard and kind of abstract question, but let me just show this quick thing. It's a cornerstone of precision measurement. So it's a very, very cute little proof with extreme power. In fact, there's a quantum version of that which exactly uses the same part of the proof to get to there. And it actually, this Kramer-Rao bound. And what is this bound? You're trying to bound that precision delta theta that we are after, or theta 1 and theta 2's variance. So this Kramer-Rao bound firstly works for unbiased estimators. So what does unbiased estimator means? It means that you have this best estimate, whatever you have done with maximum likelihood, that Fisher statement, theta estimate, a function of the data sets. If you actually calculate the expectation value of that, that should be equal to theta. Right? That's the unbiased estimate. There should not be any bias. There should not be any shift. The morning we were calculating this y's and so on, and we saw shifts. So there should not be a bias. So if you start with that, and then some little things, you basically say that, okay, del theta of theta estimate is then 1, which is nothing but writing del theta of p theta x theta estimate. I'm again changing notation. So this is basically the same as px theta and so on, like, you know, like the same thing. So or the likelihood function. You know, theta is a function of xd. All are like interchangeable. I think everyone now will probably understand. So this is the part you have, and then you can actually do a little shift. You realize that firstly, you know, you can write this as so you see that the derivative, this is a function only of the data point sets, theta estimate. You're estimating by combining your data points. The only function of theta is actually p theta. So the derivative acts on p theta. So it goes inside. Furthermore, you see that you can, in principle, this theta estimate, you can actually subtract a theta from here, because you will end up adding like theta, p theta, x, you know, and and basically the theta comes out. So you basically you're left with something like del theta of p theta, which is basically del theta of 1. So you're adding 0. It doesn't make a difference. So basically you can rewrite this structure, and that is the only kind of catch or trick that they used Sourav first, that you basically write this as theta estimate minus theta, you know, and this del theta is acting on p theta. So in fact, I can actually do a little more. I can write this as log of p theta, so that will require a one extra p theta. So p theta x dx. If you see, this is just writing this, that, there's nothing more, and there's this extra term which has been added, which is theta, p theta, d theta, and this is identically 0, so it doesn't make a difference. So this actually, right away you can see that this way of writing, and this is a very tricky way of writing, something very simple, but this actually starts looking like an average of A and B, p theta, d theta, dx, right? So this is just an average, you know. So this basically quantity just looks like AB average, right? If I call them AB. And the moment you start seeing them as average of two things, you realize that, you know, you can use something like Cauchy-Schwarz, right? Like Cauchy-Schwarz inequality, you would like to optimize this. So, you know, you're trying to find a bound on this. So you can use Cauchy-Schwarz, which I don't know, like many of you might be familiar. A very simple version of that is basically if you have like A and B, two vectors, you know, you A dot B square is basically always less than equal to A square, B square, like for vectors. And the same thing you can do for averages of probabilities. So if you do that, it's just basically the Cauchy-Schwarz version just becomes AB square should be less than equal to, you know, A square average and B square average. And this is kind of a very, very critical point. In fact, you know, just remember that Kramer-Rao bound, you will see over and over again. You will probably see it in the very next talk that Girish Agarwal will be talking about. You know, this is a very important bound, kind of a pillar of precision measurement. And there's a very clever Cauchy-Schwarz being used. So remember Cauchy-Schwarz, the term, you know, and basically there's a quantum version of that which becomes so powerful because this Cauchy-Schwarz used in that quantum version actually helps you optimize over all possible quantum measurements, you know, all possible valid quantum measurements that you can do, and still like with a simple inequality step. So, so with that, sorry, I'm rushing a bit, but we'll hopefully have a few minutes to discuss. So actually you start seeing that if I put this, A is this quantity, so A square and B square, you know, so A square average, you see, is basically just theta estimate minus theta, the parameter square, p theta dx. This is A square, and then B square is del theta of log of p theta x p theta x dx. This should be, greater than equal to that quantity, which is also was equal to 1. And we are almost home. We basically realize that this quantity is just variance of theta estimate. Again, the same thing that we spend a lot of time in the morning discussing. So you see basically that, and this quantity, let me just call it. See that it's a function of theta, x is being integrated. So let me call this quantity just I theta x. So variance of theta estimate is greater than equal to 1 over I theta x. And this is basically, it's telling you a lower bound. It's telling you that when like the best you can do for estimation is actually set by something like this I theta, which you see are actually derivatives of the probability distribution function. In fact, this quantity I theta is what is called the Fisher information. And you can, so this is basically I think the way we have it is del theta of log of p theta square p theta dx. But you can also equivalently show, again, like just using the fact that integral of p theta is 1, you can show that this quantity is also equal to actually del 2 log of p theta delta theta square times p theta dx. And so you see that whatever it is, the bound is actually set by, like, this is one way to understand. Of course, you need to work it out yourself to actually really get through it. But we have a bound on the estimation we are doing that is given by maximum likelihood. And it is bounded by a function of this maximum likelihood. You can write it in different ways. And you see that this particular one is very suggestive. It's actually telling you that, it is really the maximum likelihood's curvature. The second derivative of maximum likelihood. So it is actually telling you something very interesting, that depending on your maximum likelihood function, how well you can estimate, how well you can combine the data to have that, actually depends on the curvature. So for example, you might have different kinds of function. The one which has the steepest curvature is the most selective, because you can see that the one that has the steepest curvature is seriously like zooming into that parameter. So it has, like the sharper the curvature you have, the more selective you are on picking up the parameter, as opposed to something like this. And that is basically what is exactly captured in Rao bound, that you are bounded in your estimate by the way the likelihood function is changing as a function. Sorry, so I said a lot of things, didn't allow much questions, but now we can ask some, like we can have some discussions. And there's a very cute little paper. The plan really was to do that paper. It's in fact, like there very rarely in science you will find tentative papers, as in great people openly thinking, clearly saying that I do not have an idea, let us see what is going on, let us try to understand. And this paper is like that. And many of these things that we are talking about, you will see that how beautifully even the classical estimation and so on are written, saying that, and finally the paper concludes also, we don't know, but shows something very beautiful. I'm realizing that I'll not have time, but the whole plan was to really do that particular paper. Let's see if I can in 5 minutes summarize, but this is an extended reference to this one. Do I have that? So this is Wooter's We are basically at this stage all set to look at this paper. This is PR theta. Sorry, this is PRD. So this is a paper. You should please look at this. It's a very early on paper, even before properly the quantum Cramer-Dow bound and so on are developed. And Wouters was basically asking, another way of looking at parameter estimation, which is basically that you see that this p thetas, these probabilities. So I have a particular probability. In fact, you can see it here. So I have a particular distribution. Every point is a probability distribution here. So I have a distribution for here, and I have a distribution for there. How well I can differentiate the two distributions, how close they can be, and still I can actually differentiate. And he found something quite amazing, and he kind of openly is speculating that I don't know why this is happening, but this is true. That he basically was comparing, comparing this measurement that we also talked about. We are setting up the stage, but ran out of time. That so this very simple measurement, you are actually rotating this, and you have a cube, and you basically measure counts on D1 and D2, and from there you try to guess what is this angle someone has set, right? Like, so people might play a game with you saying that I have two angles, θ1 and θ2, just like those things. You choose like which one is the closest, or what is the game, right? And if you basically take this example and along with that take a coin tossing example and ask this question. Coin tossing is also identical, right? Like you are basically each of these, either you are seeing a click or no click, so you're like head or tail. And if you actually ask like how far these probability distributions are, like kind of like in this likelihood space, how far they are, and still you can differentiate θ1 and θ2. So what's kind of the graininess of this kind of curves, like till you can differentiate. And what he finds very interestingly is that if you do it for a coin toss, it's a very complex function. But if you do it for this photons, actually the distance, the probability distributions, very abstract thing, turns out to be exactly equal to the Hilbert space distance. It's actually exactly θ1 minus θ2. And this was his main conclusion, that statistical distance between probability distributions, the kind of curves we are drawing, are actually basically equal to Hilbert space distance. And he sets that up very, very beautifully. I'm saying that like I can take another 10 lectures and would never have that kind of fluency that Wouters had in the paper, and that honesty that he's saying, I don't understand. We are trying to find something in quantum estimation. This is the result I am getting. I don't know why quantum distributions, it's just so neat and clean. It's like just, distributions within probabilities, which are like very complex, is actually just like θ1 minus θ2. It's quite magical. And it's actually like I could have done it like, it's really like 3-4 lines, but I think it's kind of coming to an end. So any questions? Like, this is just motivation for you to go and read these things. And these are very, very important. All of us, the kind of experiments we are doing, we are getting into more and more, these things will be important. So, yeah. So, and just another point, since today, right after this, there is a lecture on quantum metrology. I don't know what Girish Agarwal will talk about, but you will see that these concepts come back over and over again of this Fisher information. In fact, this Fisher information forms there is a corresponding quantum Fisher information. And if you have, there are many beautiful properties of Fisher information. You can see this log behavior makes Fisher information additive. So if you have like n samples, this actually just becomes, 1 over n I theta x. And that basically gives you that square root of n, like, the standard deviation of theta is basically square root of n I theta. you know, and this square root of n is what we were dabbling before. This I theta is the inherent part, you know, like there were a lot of questions in the morning. It's always difficult to say case by case basis whether it's instrument fluctuations and so on, but here you have a very unified structure which you can state. And the game of quantum metrology is actually to find, you know, what is the maximum I theta that you can get. And you basically find that classically you cannot really maximize it. The upper bound of Fisher information is really a quantum calculation, a quantum model, and that will give you non-trivial scaling of n. It's a better scaling. Yeah, I think I'll stop here. Yeah, I got that. Yeah, any questions? Sorry, it was very, very rushed, but yeah, at least I could, in principle, come to the end. The most important, I think the most important of everything I wrote are the references and that Wooter's paper. Please do look at it if you find these things exciting and interesting. But yeah, they are kind of, in some ways you can say that these are some of the most fundamental questions as physicists we do. We are, finally, physics is an experimental science, and we are basically, the better we measure, the new physics we see and the more we see. So this is very important. And there will be a very interesting talk right after this, exactly on this topic. Any questions? Everything went crazy? Nothing made sense. There were so many nice questions in the morning, and I think I killed all that by going too fast. But yeah, but I think that was good, like in the morning, I think. But you know, we are paid for lectures, so we need to cover a few grounds, which is such a meaningless thing. It's far better to have questions. Okay, but if not, I think I'm already 15 minutes past. When is the next talk? 7? So I should stop. Anyways, I think everyone is saturated, the way Sourav was saying. Nothing is going on. Everyone is two-level system. Okay, so thank you. Thank you.